Hi everyone, my name is Siavash and I'm going to present one-shot imitation from observing humans via domain adaptive meta-learning. The outline of my talk is as follows. I will talk about meta-learning, the problem definition, network architecture, experiments, and the conclusions. So what's the problem that we want to solve? We are given a video of a human performing an action, and we want the robot to infer that action and performs it by itself. For example, if in the human demonstration, the human pushes the red thing to the left, we want the robot to just look at one demonstration and realize the task. And if the human pushes the bottle to the left, the robot should understand and perform that. So we want to learn from very few demonstrations, and we want to instantly generalize to new situations. There are some approaches to solve imitation learning. The simplest one is supervised learning. We have just a neural network and the output is the action and takes the current observation and state of the robot as input and then decides on some action. For example, push the hand to the left a little. Then we apply that action on the robot's arm and again give this new state to the neural network, and it gives us another action until the task is performed.
So the new image.
Yeah, new image. And we use backpropagation for that, but the problem is it requires lots of demonstrations, and if we want to perform the task on different objects, we have to train from scratch. Another approach is time contrastive networks, which we discussed in the first lecture, and the idea was to learn embedding between robotic and human domain, but still it again requires lots of demonstrations, and again for different objects we need to learn new embeddings. And another approach is meta-learning. The idea of meta-learning is learn to learn new settings. So by using prior knowledge built up from many other tasks and experience from other tasks, we want to just look at a new task and learn it from just one demonstration. Now let's take a look at our data set. We have different tasks. For example, task 1 is to push left the pack, and task 2 is to push left the cup. And we call the human demonstration DH and the robot demonstration DR. And we have many different tasks, and for each task we have a robot demonstration and a human demonstration. And the one-shot learning means that we are given just a human demonstration and we want to understand that task and perform.
So that will be, so we did build different tasks, we push left bottom.
Yeah, right? Yes, a new task that has not been seen during training. Now let's define the problem mathematically. We have a set of tasks, Ti, and each task has a human demonstration and a robot demonstration. And human demonstration are just observations from time step 1 to time step capital T, which are video frames. And robot demonstrations are a sequence of observation, states, and actions. Observations are the video frames of input camera of the robot. States are the joint angles of the robot. And actions are the torque and force applied to joints, and also the gripper if it's open or closed. So our goal is to learn a policy. What is a policy? A policy pi is a neural network which takes as input the state and observation and tells us what action to perform. And the parameter of that neural network is theta. After learning the policy, if we have a policy, we want to know how good is that policy. So we need something to evaluate that policy. And we use LBC or behavioral cloning laws to evaluate a robot demonstration. And we can use this formula to do that. And this formula actually tells us how our policy matches the robot demonstration. So the robot demonstration, some person controlled the robot and performed the task. Now we have this formula for behavioral cloning loss. But also we need to know how our policy matches a human demonstration. We want to know if our policy is good for a human demonstration or not. And we do not have the actions and states of human body, so we cannot use a mathematical formula for that.
And
Instead,
the reason that you want it makes it human demonstration because when you do one-shot learning, then the only human demonstration.
yeah, that's our only input, and we need to somehow know if our policy matches that human demonstration or not.
Robot can do that.
Yeah. So the idea is to learn it through meta-training. So our overall training objective is as follows. We have many different tasks, and for each task, we have human demonstration DH, and we have robot demonstration DR. Now suppose that we know how to calculate this L psi for human demonstration for our initial parameter theta. Assume for a moment that we know how to calculate this function.
So it's a loss.
Yeah, this loss, yeah. And by performing gradient descent on this loss, we can achieve to another parameters for our policy, which should better for this human demonstration. And by calculating behavior cloning loss for the corresponding robot demonstration for the same task, we can calculate this mathematically, and we want this to be minimum. We want this term to be minimum, this LBC. So our goal is to learn parameter theta initialized somehow that we can perform gradient descent on it based on some loss, and then the theta will achieve to some new parameter which are very good for the robot demonstration. And we can calculate this outer objective mathematically. So by backpropagation, we learn two things. One of them is parameter theta, and the other one is a psi parameter for our loss function. So by backpropagation, we learn those two things.
And so you can go back, so you will do this summation for each task.
Yeah.
You will have the demonstration of the robot and demonstration of human. You will do this all.
Yeah, exactly. For all tasks, we want to find this theta parameter which is good, which is not good for only one specific task, but is good to perform gradient descent on it and adapts to a new task. So our network is like this. During the training, our network wants to predict an action, and it takes as input the human demonstration, and then it takes the robot demonstration of the same task, and then we give another human demonstration and another robot demonstration, and we feed it all of our data. Then during the test, first we give a human demonstration, and it's the only thing that we give to the network, and it looks at this human demonstration and process it. Then we give the robot observation. Notice that this is not demonstration, it's just the current state of the robot observation. And we give it to the network, and network tells us what action to perform. And we...
One thing there, can you go back? So this testing is really a one-shot learning.
Yeah, because it just takes as input the human demonstration. One human demonstration.
Because that's why it's called meta-learning.
Yeah.
That we have done once using human and robot demonstration on these tasks. Now we have new tasks, then we can learn on top of it just one. And that can be like a testing for what we have done. So it's one is very careful to talk about that.
Yeah.
And actions, you mean the robot joint angles out of
The force and torque applied to robot joint angles, and we do that, and we perform that action, and the robot performs that action, and now we have a new robot observation, and then again we feed it to the network, and it tells us to perform another action until the task is done. Now let's take a look at the algorithms for this. So one algorithm is meta-imitation learning from humans. It's the meta-training part. It requires the human demonstration and robot demonstration for each task. And it also requires two hyperparameters, alpha and beta. And during the training, we just pick up one task or a mini batch of tasks and pick the human demonstration. Then we calculate, if we apply gradient descent on this demonstration based on this L psi, then we calculate the new policy which should be good for this task. Then we look at the robot demonstration and apply gradient descent on this LBC, which we can calculate mathematically. And in this LBC, the L psi is expressed. So we can use just gradient descent on this LBC and we learn theta and psi. And then we return the theta and psi parameters.
And you do this for every task, right?
Yeah, during the training, we just pick up different tasks and maybe a batch of tasks and we perform and we do this for them. And after we learn theta and psi, we need this algorithm to adapt to any new task or human demonstration. This other algorithm is called learning from human video after meta-learning. And we know the parameters theta because we learned them from the previous algorithm. We know L psi. And we also have one video of human demo DH. And we want our robot to look at this and learn to perform the task.
So that's why it's called one-shot learning.
Yeah, it's one-shot learning. Yeah. And in order to achieve that, we just simply perform gradient descent on parameter theta based on L psi. And we know L psi and initial parameter theta, and by performing gradient descent, we just achieve to a new policy parameterized by phi, and we just return that policy. Now let's take a look at our policy network. So first we have a human demonstration, and we apply some convolution layers on it. So these convolutions are 64 3x3 convolution layers, and the first three have a stride 2 and the last two have a stride 1. Then we apply a spatial softmax, which we'll discuss later, but it extracts 2D points from each channel. So if we have 64 channels, we have 64 multiplied by 2 feature vector f. And then we send this feature vector through some fully connected layers with ReLU activation. And this architecture, and we concatenate the last hidden layer with F, and this is a two-head architecture. So the human demonstration starts from here and goes all the way through this head, and it never goes through the other head. So it's a two-head architecture. And right now we just want to look at this 1D temporal convolution as a black box. It just calculates L psi for us. And after calculating L psi by backpropagating, it gives us the inner gradient which we can use to adapt our policy to this task. Then we have the robot demonstration. We send the robot demonstration through the same convolution layers, and we also concat the robot state, the current state of the robot, and we try this to use these features to predict the gripper pose. So we just send these features, and this is a fully connected layer, and it tells us what should be the gripper pose.
So robot state is the torques and joint angles.
Robot states are the joint angles, yeah. And the predicted gripper pose tells us if we should open the gripper or not. And we also have, from the demonstration, we know what is the robot gripper pose. So we can easily calculate the squared error for this. We also, because the actions are more complicated than just the gripper pose, we also use these ReLU and fully connected layers to also predict the more complicated actions, which are forces and torques applied to robot joints. And we have the robot demonstration action, and we know what was the actual action that performed, and we can also calculate the LBC loss. So we calculate this LBC loss, and we update our parameters theta in order to be more optimized for adapting to new tasks. Now let's take a look at this L psi and see how does this 1D temporal convolution work. Oh, before that, during the parameter adaptation, we just perform gradient descent on our initial parameter theta based on this L psi, and we just adapt to the new parameter for the other task. So now let's take a look at this temporal convolution network. This temporal convolution network takes the last hidden layer of previous network, as I showed. So the last hidden layer from time step 1 to time step capital T are fed into this neural network. Then we stack all of those features on each other and create a matrix. And the height of this matrix is T1 until T capital T. And these are just all the features of all the time steps. And the last hidden layer length is 74 here, and that's the length of these features. Now we want to apply convolution through time. So in order to achieve from here to the next layer, we have to apply convolution through time. How does that work? We have a 10 by 1 convolution, and because our time is just one dimensional, so we just put this mask on 10 time steps and multiply them all element wise and sum them together, and it gives us the corresponding element in the next layer. Then we shift this mask one level up, and then we again multiply them all together and sum them, and this gives us the next element. And if we do that for all the elements here and use the same padding, so we have one column for one mask. Then we use another mask and again do the same thing and multiply them and sum them, and it gives us corresponding elements. So the length of the next layer is equal to the number of masks through the convolution, and we use 10 convolutional masks. So this one is 10, and because we use the same padding, the height is still capital T. Then we again apply 10 by 1 convolutions on this layer. So because we apply 10 masks, the next layer also has length 10, and the time steps are again, because they use the same padding, are capital T. Then we use 6 1 by 1 convolution. So 1 by 1 convolution just looks at one time step at a time and calculate the corresponding. And because we use again 6 masks, the output length should be 6 and its height should be capital T. Finally, we just apply a norm on this matrix, and it gives us just a number, and that number is L psi. Then we backpropagate this L psi through all these layers by backpropagation, and we backpropagate through the previous network that I showed.
Maybe you can show that, go back to that and show them the other.
Yeah, here this backpropagated loss is the inner objective or inner gradient for this network. And we just discussed this. Now let's talk about a spatial softmax. There was a layer in the bigger network that was a spatial softmax. So if we have this input and we want to know where the maximum is, we can use argmax, and it tells us it's in row 0 and column 1. But argmax is not differentiable, so we cannot use it in layers of our neural network. So instead of doing that, we use a spatial softmax. The first step is apply ReLU, which makes these negative elements 0. And then we apply softmax. And softmax is calculated easily by this formula. So the sum of all elements in this matrix is 1. Now, in order to find where the maximum is, we just apply expectation in both axes. So let's start with the x-axis. The expectation formula is as follows. The Sij is the output of softmax for element ij, and I is just the row number. So here it is the row 0, this is the row 1, and this is the row 2. And we just multiply these rows with their row number, these values with their row numbers. And it gives us a number. And this number is near 0, where was the maximum. And this is our fx. And then again we do the same thing in y-axis. And here we have column 0, column 1, column 2. And we multiply these elements by their column number. And it gives us a number. And this is the output of our spatial softmax. As you can see, these numbers are close to argmax, because our maximum is here and the next maximum is here. You can see that fx is 0.433, which is between 0 and 1. And fy is 1.159, which is between 1 and 2, because our maximum is in column 1 and the next maximum is in column 2.
So the main thing is that for every channel they want to find out location X, Y, coordinate of the location where it's maximum.
Yeah.
And that's like a feature representation of each of channel, and somehow those are important
Yeah.
for the rest of the network. And since all networks are non-differentiable, so you have to go through all those things.
Yeah. Now let's talk about the experiments. The goal of the experiments is to check if this method works and if it can be generalized, and comparison with other meta-training approaches, which are contextual policy, DALSTM policy, and DAML linear loss. This is just our approach, but without temporal convolution network. We just apply a fully connected layer and take the norm of that instead of using that 1D temporal convolution network. And this is the approach we discussed. What are the tasks we want to what are the tasks? One of them is placing, and during training we have 293 of human and robots demonstrations, and we test on 15 different objects which never seen during the training. And we perform one-shot learning, and we have to place a held object into a container while there are two other containers, and we have to avoid those two distractor containers. So here we should put this object, Apple I think, we should put this object into the container, and we should not put it into two other distractor containers. Another task is pushing, and they use 640 of human and robots demonstrations, and they use 12 different objects which never seen during the training. And again, they use one-shot learning, and the task is to push an object to the left when there is another object on the table.
So for each of these 12 objects, there's only one video.
Yeah, that's one-shot learning. They just, for the test, they just have one demonstration of human pushing something to the left. Another task is pick and place, and then again they use 1008 of human and robot demonstrations, and then they test on 15 different objects that they never seen during training, and they again do one-shot learning. They just give one human demonstration of the task, and the task is to pick something and place it into some container, while there are two other distractor containers. So here the user has to pick this thing and put it into this container and not into those two other containers. Now, what are the objects they used for tasks? These are some subsets of their objects. So for the task of placing target, they used these objects for training and used these objects for testing. So these objects were never seen during training. And for holding objects, they use these objects for training. Actually, this is a subset of the objects they used. And these objects for testing. And for pushing objects, they use these objects for training and these others for testing. Here's a video of their experiments. Here, the task is to put the thing into the red container, and you can see that other approaches cannot work as well as our approach. And if the person puts the thing into the red cup, now our approach looks at this demonstration and performs the action. And if the task is to put into the white plate, you can see this contextual and LSTM require lots of data in order to be able to perform those tasks, and do not work well on different objects. This is the pushing experiment. In human demonstration, we push something to the left, and the robot should infer that. So you can see these other ones try to push the red thing, while the target was the blue object. You can see that this method works pretty well by just looking at one human demonstration. And the last task is pick and place experiment. And here in human demonstration we pick something and put it in the white plate. And you can see these two approaches require lots of data. and temporal loss really helps. Now here the container is this object, and you can see these other approaches just put it into another container. They cannot distinguish the task, what containers they should put the object
So
in.
here it fails or something?
Yeah, sometimes it fails. Yeah. Yeah, here's, and that's, and this is the table of the results, and you can see that they achieved very good success rate performance. And the other experiment was to check if what happens if we have a large domain shift. So they just consider the pushing task, and they use another camera, which is just a mobile camera, and perform the task in a different room with a different perspective, and they used 10 different table textures. And during the training, the human just performed the task on different table textures from different perspective, and during the test, the robot should perform the task on the green table. And also during the test, they used 3 different backgrounds. One of them was seen during the training. 2 other novel backgrounds were never seen during the training. And this is their experiment with this large domain shift. So these are 2 different tasks. One of them pushed the red cup, the other pushed the other object, and the robot can infer what was the task. And here is the novel background that the robot has never seen during the training. So this is the table of the results. As you can see, when they change the background, the accuracy decreases, the success rate decreases. And they also show their failures, and they do not just consider success and failure. They define 2 types of failures. One of them is from task identification, which means the robot even did not understand that it should perform the task on the red object, for example. And the other type of failure is from control, which means the robot tried to push the red thing, but it couldn't do that well because of the control. And another experiment is on Sire robot. They wanted to see if their method works well on different robotic arms. So a Sire is just a robotic arm, and they put the camera here, and again collected train and test robot demonstration and human demonstrations. And this time for their success rate, they used 3 trials. So the robot tries 3 times. If one of them were successful, they report it as a success. So this is the experiment on this Sire robot.
So the reason they do 3 because it's harder than the other one? Or?
Maybe, yeah, maybe there. As you can see, the robot can infer by just looking at one human demonstration. So they achieved to a 77.8% success rate, and they had 18 held out objects. These 18 objects were never seen during training. So conclusions are: learning from human demonstration. We had a method to learn from human demonstration by using meta training, and also we showed temporal adaptation loss helps. And there are also limitations for this method. The behavior at meta test are structurally similar to meta train, and lots of data required for meta training still. It's true that we can use just one human demonstration to adapt, but for learn to learn, we need to look at lots of data. And they say that we can use it beyond human imitation. We can imitate animals or also simulated robots from simulation. and we can infer information from out of domain. And that's it.